Hello and welcome back. The last video I talked about nomenclature, structure and physical properties of carbonyl compounds. In this video we will see some techniques to prepare them, and in the later part of the video we will see some common uses of these compounds. So let's get started. First we will see some common techniques to prepare any of aldehydes or ketones. First we have oxidation of alcohols, then dehydrogenation of alcohols from hydrocarbons, which includes by ozonolysis of alkenes, by hydration of alkynes. Then we will see some techniques that are specific for aldehydes, which includes from acyl halides and from nitriles and esters, then from hydrocarbons, which includes by oxidation of methylbenzene, by side chain chlorination followed by hydrolysis, by Gatterman-Koch reaction. Then we will move on to see some techniques specific for ketones. First in this is from acyl chlorides, then from nitriles, and finally from benzene or substituted benzenes. You might have seen some of these in the previous units or in previous class. So in such cases, I will just be mentioning that this has been seen in previous class. Just a reference will be given instead of a detailed content. So first in the line is by oxidation of alcohols, which we have seen already in class 12 unit 11. Aldehydes and ketones are generally prepared by oxidation of primary and secondary alcohols respectively. Then we have by dehydrogenation of alcohols, which again we have seen previously. This method is suitable for volatile alcohols and is of industrial application. In this method, alcohol vapors are passed over heavy metal catalysts like silver or copper. Primary and secondary alcohols give aldehydes and ketones respectively. That means primary alcohols gives aldehydes and secondary alcohols give ketones. This has been covered in unit 11 of class 12 in detail. Next, from hydrocarbons, and first in that is by ozonolysis of alkenes, which was again covered in class 11 unit 13. As we know, ozonolysis of alkenes followed by reaction and with zinc dust and water gives aldehydes, ketones, or a mixture of both depending on the substitution pattern of alkene. But since this is of significant importance, I am mentioning an example for your reference. In the example, I have taken 2-ethyl 3-methyl but-1-ene and I have subjected it to ozonolysis. I get two products, that is on the top, one on the left and one on the right. One of them is ketone, that is on the left, and the other one is a aldehyde in this case. Yeah. So the other one from hydrocarbons is by hydration of alkynes. Addition of water to ethane in presence of H2SO4 and HDSO4 gives acetaldehyde. All other alkanes give ketones in this reaction, and this has been covered in detail again in unit 13 of class 11. Next, we will move on to preparation of aldehydes, and first from acyl chloride. Acyl chloride is hydrogenated over catalyst like palladium on barium sulfate. This reaction is called Rosenmund reduction, and this is an illustration of such a reaction. When we have taken the reactant that has an acyl chloride and subjected it to hydrogenation with palladium on barium sulfate as catalyst, we get a benzaldehyde. Next, from nitriles and esters. Nitriles are reduced to corresponding imine with stannous chloride in the presence of hydrochloric acid, which on hydrolysis gives corresponding aldehyde. This reaction is called Stephan reaction. For example, I have taken arsen with SnCl2HCl, that is stannous chloride in presence of hydrochloric acid. I get RCH double bond NH, that is called imine, and upon hydrolysis of imine I get RCHO, that's an aldehyde. And alternatively, nitriles are selectively reduced by diisobutyl aluminum hydride, that is dibal H, to imines followed by hydrolysis to give aldehydes. So similarly I can take ACN subjected to dibal H, then I hydrolyze it to get RCHO. The intermediate is again imine, that is when I subject ACN to dibal H I get an imine, and when I subject that to hydrolysis I get RCHO. In fact, dibal H is chemoselective, that is double bond is not reduced in the example that I have given here. CH2 CH double bond CH CH2 CH2 CN, when I subject it to dibal H, the double bond is retained. So this compound is useful when we need to reduce cyanide to CHO when there is a double bond like this. Similarly, esters are also reduced to aldehydes with dibal H. So ester RCOOR dash with dibal H followed by hydrolysis I get RCHO. Next, from hydrocarbons, aromatic aldehydes and its derivatives are prepared from aromatic hydrocarbons by the following methods: by oxidation of methylbenzene, by side chain chlorination followed by hydrolysis, by Gatterman-Koch reaction. First we will see oxidation of methylbenzene to obtain aldehyde. Strong oxidizing agents oxidize toluene and its derivatives to benzoic acids. However, it is possible to stop the oxidation at the aldehyde stage with suitable reagents that convert the methyl group to an intermediate that is difficult to oxidize further. The following reactions are used for this purpose: use of chromyl chloride, otherwise we can use chromic oxide, and we will see each of this in detail now. Chromyl chloride oxidizes methyl group to a chromium complex, which on hydrolysis gives corresponding benzaldehyde. This reaction is called Ithard reaction. For example, let's consider this reaction. We have toluene with CrO2Cl2. I get an chromium complex, that's an intermediate. When I treat it with CrO2Cl2 in presence of CS2, that's a solvent, the toluene gets converted to a chromium complex. Then when I hydrolyze it, I get benzaldehyde. So similarly CrO3 now, toluene or substituted toluene is converted to benzaldehyde diacetate on treating with chromic oxide in acetic anhydride. The benzaldehyde diacetate can be hydrolyzed to corresponding benzaldehyde with aqueous acid. So for illustration, I take toluene in CrO3 acetic anhydride at 273 to 283 Kelvin. I get benzaldehyde diacetate as intermediate, which upon hydrolysis with aqueous acid I get benzaldehyde. Now by side chain chlorination followed by hydrolysis. Side chain chlorination of toluene gives benzyl chloride, which on hydrolysis gives benzaldehyde. This is a commercial method of manufacture of benzaldehyde. So this is toluene with chlorine in presence of light. I get benzene with CHCl2. Upon hydrolysis at 373 Kelvin, I get benzaldehyde. Another reaction is Gatterman-Koch reaction. When benzene or its derivative is treated with carbon monoxide and hydrogen chloride in presence of anhydrous aluminum chloride or cuprous chloride, it gets converted to benzaldehyde or substituted benzaldehyde. This reaction is known as Gatterman-Koch reaction. For example, I have taken benzene, treating it with CO, that is carbon monoxide, and hydrochloric acid in presence of anhydrous aluminum trichloride or cuprous chloride. I get benzaldehyde. Yeah. Now we are going to prepare ketones. First, from acyl chlorides. Treatment of acyl chloride with dialkyl cadmium prepared by reaction of cadmium chloride with Grignard reagent gives ketones. So first we will see how to prepare this dialkyl cadmium. We take Grignard reagent, that is RMJX, and treat it with CdCl2. I get R2CD plus some byproduct, that is MgXCl. So this R2CD is dialkyl cadmium, that is what we need. So now I take this R2CD and treat it with RCOCl, that is acyl chloride. I get R-COR, which is the ketone which we desire, along with CdCl2 as byproduct. Now from nitriles. Treating nitrile with Grignard reagent followed by hydrolysis yields a ketone. We have the example over here. We have CH3 CH2 CN and treat it with IMGBr, that is the Grignard reagent. In terms of ether, I get an intermediate, which upon hydrolysis I get the ketone that I need. From benzene or substituted benzenes. When benzene or substituted benzene is treated with acid chloride in the presence of anhydrous aluminum chloride, it affords the corresponding ketone. And this reaction is known as Friedel-Crafts acylation reaction, which you have seen many times, I suppose. And this is the reaction. We have benzene. I treat it with acyl chloride in presence of anhydrous aluminum chloride. I get the corresponding ketone. So with that we have finished different ways of preparing aldehydes and ketones. Now we will see some uses of carbonyl compounds so that we have some purpose of preparing this. In chemical industry, aldehydes and ketones are used as solvents, starting materials and reagents for the synthesis of other products. Formaldehyde is well known as formalin, that is 40% solution used to prepare biological specimens and to prepare bakelite, which is a phenol formaldehyde resin, urea formaldehyde glues and other polymeric products. Acetaldehyde is used primarily as a starting material in the manufacture of acetic acid, ethyl acetate, vinyl acetate, polymers and drugs. Benzaldehyde is used in perfumery and in dye industries. For example, vanillin, that is obtained from vanilla beans, salicylaldehyde obtained from meadow sweet, and cinnamaldehyde, that is obtained from cinnamon, have very pleasant fragrances. Acetone and ethyl methyl ketones are common industrial solvents. Many aldehydes and ketones are well known for their odors and flavors. Some of them we have seen in the previous slide also, like vanillin, and some I have given here like camphor, which you have heard before. So with this I have come to the end of this video. To summarize, in this video we saw some methods to prepare carbonyl compounds and then we saw some uses of these compounds. The next video we will see various chemical reactions that these compounds undergo. I hope the content in this video was clear and I hope to see you in the next video. Goodbye.